Okay, the goal for today, we're going to review the composite design pattern that we finished last Wednesday. And then we're going to go for the, to my opinion, the most exciting design pattern for the course, which is called Visitor. We'll get there. And just to remind you, on the lectures page, as I mentioned last time, you may actually want to try out this particular tutorial video series, which will actually build your programming skills for the visitor pattern from scratch. Okay, follow that, and then hopefully that can help you understanding about the visitor and composite pattern working together. Okay. All right, so from last time, we actually talked about the composite design pattern. So let's just review very quickly. I promise I'm going to go over this slide the last and then try to review what a composite pattern is. And then one of you actually asked a very good question about self-loop for the composite design pattern. Because remember, composite design pattern is meant to build a tree. But what if you got a self-loop? Or what if you got a cycle in your particular tree, which is not a tree anymore? It's more like a general graph, right? I'll mention this question a little bit later. I do have something prepared for you. Okay, let's just go over, just review the composite design pattern very quickly. So from the design point of view, so when should you use the composite design pattern? Basically, every time if you got a notion between base and recursive artifacts in your particular system, it can be equipment, it can be furniture, or it can be, when we talk about a visitor pattern, we're going to talk about a more CS or engineering-oriented example, like a language. Okay, we'll get there later. But anyway, from the design point of view, every time you see the notion between basic versus recursive, then you should really use composite design pattern. From the programming point of view, all you want to do is build a tree, and then how you can use an add child and also use generic classes to satisfy the single choice principle, etc. Okay, at the runtime, how is it going to work? Okay, let me just mention the point here, and then we can review what we did last time very quickly. So at the runtime, you want to allow the clients to treat base objects and recursive compositions uniformly. So what do I really mean by that? Okay, before I get to the example, let's review what we did last time. So we can talk about polymorphism, and also we'll talk about dynamic binding, right? You can review the recording from last time. For our particular example, let's say, if I declare E of static type equipments, right? So that means from the composite point of view, if I declare, simply say E is of type equipments. Over here, you can see equipment is exactly on the top over here. So that means for E here, I definitely can always say E the price for sure, right? However, E the price might refer to maybe the price of some basic unit. It could be, for example, 200, right? On the other hand, the price is also available to the composite equipment, and for which, for example, cabinets. And for the cabinets, it also has a children list, right? For every composite equipment, we also got children. So now in this case, maybe for cabinets, if you think about it's a tree, right? Cabinets might have 3 different children over here, and maybe the first child is just another cabinet, and the second one might be a video card, let's say a base case, and also the third child might be a disk drive. Over here, let's say this is 200, this is 500, right? For every basic unit, you have some price for sure. And then for this first child, maybe again, it has another 3 children, right? Let's say video card, and video card. In that case, every one of them, let's say 100, 100, 100, right? So now if I say I got this particular cabinet, for example, C. If I say C the price over here, right? So basically what we need to do is to aggregate all the price together, 100, 100, 100, 200, and 1500, right? So see the price over here is referring to the root of this particular tree. But that one there is actually going to recursively calculate all the prices over here and add them up together. So that's the example we did last time. Okay, let me just go back to the slides, right? So when you study this particular slides, so when you say E the price over here, depending on the dynamic type for E, the dynamic type for E could be maybe the cabinets, right? Over here, that could be the top level. Or E the price over here could also be, for example, E the card over here, right? You can see it's one of the basic units. In that case, you will be returned a price rather than having further recursive calls to the price. Okay, that's a very quick summary of what you got last time. And let me just go back to the diagram over here from last time very quickly, right? I'm not going to trace it from the beginning again. I just want to write it in a fast forward mode very quickly. So now let's think about this, the same example. When you say cabinets dot price over here, so that means we're calling the price at this particular composite equipment objects, which will invoke for every element in this particular cabinet, every child. In that case, we're going to also further invoke the price for chassis over here. And then for this particular chassis, we're going to invoke this and this. So which means the price over here and also the price over here, right? And the price for this particular basic components will just return 500 eventually. And also the price for this particular composite first child over here, that one there is going to further invoke every child for that particular bus, right? And this will in turn invoke the price for this particular basic unit, which will be 200. So that is why eventually you will see 700, which is equal to 500 plus 200. Okay, that's what we talked about last time. Okay, any question about the composite? So two things for you to study for if you want to review this pattern. Number one is about architecture. Number two is about a runtime structure, exploiting polymorphism and dynamic binding. Okay, any questions? All right, I presume everybody is okay. All right, let me go to, okay, so I think now we are basically done with all the slides that I planned for composite pattern, right? That's the last slides. And of course, if you go towards the end, everything has been talked about. If you go towards the end, you will see over here, oh, sorry, the link is in the visitor pattern slides. I'll get there later, okay? Before we get to the visitor pattern, I would like to talk about one of the questions you guys asked me last time. Okay, just give me one moment. Let me just move the composite to the end, and then before I talk about the visitor, let me talk about this particular question here. So one of you guys actually asked. Hopefully you're still in the lecture today. Hopefully. Okay, let's see. The question goes like this. Apparently, composite design pattern over here, we said at the runtime, the goal is really to build a tree. And when we say tree, it's not really a graph. And the difference really is when you actually got cycle, right? That's the difference. And when you talk about cycle, it can be either a simple cycle like a self loop, right? This is like a cycle. Or it could be that maybe you have different nodes over here. So you can see, let's say, go back here and also go back here. Okay. Let's see this. You can see this is actually a cycle, right? So basically either a self loop or the cycle. So the question goes like this. In the composite design pattern, what if we got self loop? Okay, so now number one, you want to judge to see whether self loop is a good thing or a bad thing, right? Number one. And number two, if it turns out to be a bad thing, how can you prevent it at a runtime? Okay, two questions over here, right? Number one, I'll just say cycle, right? Cycle, again, it can be two cases, either self loop or a more general cycle, right? So cycle, is it good or bad? Number one, in the context of composite design pattern. Question number one, right? Think about it. I'm going to answer to you right away, okay? Just think about it while I'm still talking about the second question. Number two, if cycle is actually bad, then how to prevent the cycle for the composite pattern at the runtime, right? So two questions over here. Okay, so for number one, cycle is a good or bad? It turns out it will be bad. Okay, let me just give you one example I prepared already, a very simple example. Let's say this. Let's say over here we got C1 and C2. They were declared to be of type cabinets over here, okay? So that means you have C1 is pointing to some cabinets objects at the runtime. And every cabinet also is a composite equipment, so that will have the children, right? Initially, it's simply just empty, okay? And similarly, also for C2. C2 is also pointing to another cabinet objects over here, and also children over here. And the children list is simply just empty to begin with, right? So far, so good. After these two initialization, we got two cabinets whose children lists are simply just empty. So now what we want to see is how can we create a cycle? Let's say a simple case. Let's say you just say, if this is C1, C1's children is simply pointing to, let's say, itself over here, okay? So now what I want to do is, if I simply say C1.add C2, is this okay, first of all, okay? If I say C1.add child C2, so that means the first child for C1 is now going to point to C2. So this does not seem to be a problem. That's what we talked about before, right? On the other hand, let me just undo this, okay? This one does not seem to be problematic. Let's say that's okay, right? Let me build another example for you over here. If I say C1.add, let's say C1. Of course, here it will be quite obvious. That was intentional. You're just adding C1 to itself. But it could be maybe just another object over here that's actually aliased to the same object that C1 is pointing to. That would be the same problem over here. Okay, I'm just making it more obvious to you. Okay, so now let's say we're adding C1 to itself. So what that would do is C1 over here, the first child, is basically referring to back to itself. Okay, so this currently is permitted by our architecture over here. Okay, that's the architecture we're talking about. Because for cabinets, which is a composite equipment, we're saying that its children will just be a list of equipments, including cabinets. But we didn't say anything about the children themselves cannot be overlapping with their parents in terms of the references. That's something we didn't constrain, right? But now you can see this particular line wouldn't actually make any real sense, because how can you actually fit in a cabinet into itself? It doesn't make sense, right? So now, again, you want to say, so the conclusion for this one would be, so this is actually allowed by the current design of the composite design pattern architecture. Number one is allowed, right? But it doesn't make sense. It doesn't make sense for the reality, because how can you fit in a cabinet into itself, right? So guys, so far so good so I'm basically trying to answer number one over here. And similar argument applies to cycle, right? So now I'm just talking about self loop. Okay, apparently cycle or self loop is not good because you cannot fit in some composite equipment into itself. It doesn't make reality sense. Okay, number one. Number two, if it is bad, then how can we prevent it at a runtime? At a compile time, you don't necessarily keep track of how you're adding the children into the list because it's undecidable problem, right? But anyway, so how can we prevent this bad thing to actually happen at a runtime? How can we prevent it? Okay, the answer is you want to add in some class invariant contracts, right? Remember, one of the most important learning outcomes for this course is you want to really specify the constraints of your software or how the objects work together at a runtime using contracts, precondition, postcondition, and class invariants. And now, the kind of contract we are trying to specify really has to do with but for now, what we really want to make sure is when you're trying to create the tree structure at the runtime from the composite pattern, it doesn't really have such cycle. Okay. Christine have some question here. Let me read it out. I get that it doesn't make sense. Good. But does it have any negative consequence during the runtime? I would say, okay, when we agree that it doesn't make really reality sense, so that means you're not really programming your application consistently with the customer's expectation, right? Let's say if a customers of the manufacturer system, would they actually expect that you assemble one cabinet within itself? Actually, just not possible, right? So that means if you actually allowed this particular self loop or cycle to happen in your composite design pattern, so that means you're allowing something that doesn't make sense to happen at the runtime for your system. So that's not good, right? So the consequence would be you're just programming something that seems to work, but simply doesn't correspond to the customer's expectation. Okay, hopefully that makes sense. Good. So now, good. So now, number two. Okay, now that we understand, so number one, number two are both important, right? Number one is about why it would be a bad design, number one, okay? And number two, if it's really a bad design, how can we prevent it? Let's just talk about the self loop. Just make it simpler for you, okay? So let's say I want to constrain for every composite equipment's objects. For example, let's say an object of type cabinets, an object of type chassis, and also an object of type bus. They cannot fit into themselves, basically, right? So now, how can I specify some class invariant to constrain this? Okay, so this, I know the answer already apparently, but I would like to give you an opportunity if you want to tell me what the answer is. I can pause a little bit. Okay, that's the last topic I want to talk about for the composite before I go on to visitor. Guys, any answer you want to suggest? So now I even give you a little bit more hints. I say no self loop over here, right? And now what should I specify over here as a Boolean predicates? Okay. How can I say that every one of my children over here, none of them should be myself? Okay. It's informal what I just said, but hopefully that's give you enough hints. Okay. Anybody? Okay, what I have over here is not children that has current. That's pretty good. However, be careful over here. Okay. 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 I think I have the correct answer from over here. Okay, I got many of you. Okay, just forgive me. I'm not gonna mention your name over here. Got many answers there. Okay, let me just mention two of them. Okay, and I tell you why it may not be working so well, potentially. Okay, one of them was I can say children. Okay, let me give you two possibility. Right, if I say children over here dot has current. Okay, that's number one. Okay, that's possibility number one. And number two, it goes with a cross loop. Okay, it will simply go for across, and then we'll go for across, let's say children. Oh, okay, let me just write it down in the next page. Okay, so number one, we can say children dot has current. It is not the case. I would say that's pretty good. It's definitely on the right track. Number two I got from you guys was like this, using a cross loop. I would say across over here, children is, let's say, C. And it's a universal quantification, right? You should want to say it is not the case that, oh, sorry. It is a universal quantification to say every child is not equal to the current, right? I can say current over here is not equal to, right? I'm using tilde, right? And then I would say C over here. Okay, we got two versions over here. I would say for two versions over here they are pretty good for both of them, okay? However, there's a trouble over here. If let's go back to our let's say you can see over here C. Let's say for this particular case, right? Children is basically a list of equipments, and then C, of course, will be equipments. Okay, let's say what if I say class equipments, right? Of course, it's deferred. Okay. Remember the way the tilde actually works goes like this. If the is equal feature was not redefined, okay? If it was not, if the is equal feature in equipments, right, was not redefined, and then it would be as if we say current equals C. So this one here is really comparing the reference equality. That seems to be what we are aiming for. Okay, I would say this is two suggestions I'm writing out in orange. They will work if the is equal was not redefined. Okay, I hope you follow my point. Otherwise, if it was redefined, the is equal, then it would be as if we say currents dot is equal. And then we say C over here. And now this is not what we really want, because now this will be comparing just the contents, but not the comparing contents over here, not reference. It's no guarantee. Okay, hopefully everybody can follow this point over here. So now what's really important is this solution over here, or when you say has, also it depends on, for the children is actually a list, right? And for the collection, we also got a Boolean attribute over there called object comparison, right? That's something you want to either set or unset, but it's just a little bit more technical detail. I'm just trying to tell you that when you use either has or use a tilde over here, there is a possibility that you may not end up comparing references only. You may only compare the contents over here, which is not correct. Okay, that's my point. So what would be the correct way of saying it? Okay, let me go back there. The correct way of saying this, let me put it the final solution. Okay, the correct way of doing it would be over here. Okay, you would say across children is C. Okay, and then you would say current over here equals C. All. Okay, of course I meant not equal to. Okay, so now this will guarantee you're always comparing the reference, and then you make sure they are not equal to the parent itself. Okay, so that's just a simple contract for self loop, and I'll leave it to you to see how you can make sure there is no cycle. And of course, that will actually make a little bit more programming to be implemented. So you actually make sure there's no cycle. You may want to define that recursively. Okay, that's beyond the scope for this particular lecture, but at least you can understand how to get the self loop to work. Okay, all right. So this is like a long response to one of your questions, which I think is pretty good question. So that's why I spent the time. Okay, so that's about the composite design pattern. So now we want to move on to the continuation of that, right? Okay, let's take a look. So what I want to do now is like this. Okay, the visitor design pattern is will go like this. Okay, basically what we have already covered the composite, which is build a tree, but now building a tree is just the phase number one. You may got many potential operations you want to perform on the tree, and price is simply just one of them. And remember, when we talk about design, you always have to think about supporting in theory an unbounded number of possible operations as an extension to your design, right? Not just the current one. You want to think about for the future, what if I want to add more operations to my composite design pattern? How can I do it, right? The way we did it before, okay, let me just remind you again. The way we supported operation before goes like this. We simply put the price, for example, you can see calculating the price is just one possible operation. We simply put this operation over here at the top level for the equipment, which will force every effective descendants over here to implement it. That seems to be a reasonable solution. Of course, if you also want to calculate, let's say for power consumption, if I simply say power consumption here also will be a real number, and then I will be also forced to implement the power consumption for every one of them, right? Similar idea. It seems like every time we want to add a new operation to really somehow to calculate some property of the tree, we just add it to the top level, to the root of the hierarchy, right? That seems to be a reasonable solution. But now, the reason of having a visitor design pattern is to say that may not be the best solution you should really use when you get an increasing number of operations. Okay, let's see. So what we're going to do is we're going to use a different problem, which is more useful maybe when you implement later on for those of you who might be interested in implementing a compiler which will compile one language to another. So this will be some relevant example. But anyway, if you're not interested, we can still follow the example. Hopefully that'll make the point. Okay, let's say this. So this is gonna be the working example we're gonna focus on for the rest of the lecture for the visitor. Okay, so now based on the composite design pattern you learned from the previous one, so now we want to know how should the composite design pattern architecture look like if we want to support the following. Let's say we got 341, we got 2, we got also 341 plus 2. Let's say for simplicity, it seems like we got either base cases or we got recursive cases, right? Base cases, let's say we just got integer. For recursive cases, we can got different operations. In this case, we just support one single binary operation. Let's say just binary. Let's say plus. Of course, we can further extend it into multiplication or even ternary expression later. Okay, but for now, just make it simple. Okay, you should really ask yourself. Okay, I'm going to show you the solution right away. You should ask yourself, based on this, we got one possible base case, integer. We got one possible recursive case, addition. How should the composite design pattern architecture look like if we want to draw it? Okay, so now it's going to look like something like this. Okay, and you should really see that it's very similar to what we did previously. The only difference is, just for simplicity, I didn't have this separate composite class over here, but we should. Okay, just for simplicity for presentation, I simply put everything over here into composite equipment or composite expression. Again, that will violate single choice principle, but just for now, just for illustration. Okay, let's say this, we got expression at the top, and also let's say we just got value. Value is just to evaluate. You can think of value like it evaluates for this particular expression, right? And then we can either have constant or integer. And we also got addition. You can see these two classes are actually effective. Okay, and also we got composite over here, which is deferred. Some of you actually asked the question yesterday on the course forum, just about when should you put plus, and should you put deferred like a star over here. I would say you should really try as much as possible to put the plus, and also star to really clarify which for each class, whether it should be deferred or should it be effective, or even for the feature should it be redefined, etc. Okay, just a connection to the foreign question yesterday. Okay, so now here's a question, right? So now hopefully nobody got the question about this composite design pattern architecture here. And then what we will do is we're going to extend the composite design pattern in the following way. We want to, that's our intention. We want to support the various operations for our small expression language. You can think about this is our language here, which is just support constant and also addition. And now we want to support the various operation over here. Either we want to say, for example, just let me just get it clear for you. Okay, we want to support the various operation. Either we're going to say printing, either we can print the prefix or we can print the postfix, for example, right? So let's say this. There is some exercise over here. I'm going to leave that to you, and you will see something very similar later on, right? How do you build a tree for this particular expression, right? 341 plus 2. Essentially, you got expression over here. Under expression, you actually got addition, right? Addition can have basically left and right. You can think about left and right. Each one of them will just be another expression. And then for each expression, it will just be a constant, right? It should be, sorry, let me draw a little bit more carefully, okay? I'm just gonna sketch that a little bit, and then you can draw the more detail, okay? Let's say this. How do we represent this particular as a tree, this particular expression? Start with expression over here, and then under expression, you have basically, let's say addition. For addition, it can be left and right, right? Left and right over here. Each one of them will just be an expression. And then under the first expression will be 340. So that be under this will be constant. And under this will also be a constant. And then you got, oh, of course, I got a plus over here. I forgot, right? And also you got 341. And also here you got 2. Okay, eventually you will get 341 plus 2, right? All the leaves together, right? For those of you who actually took, if you're in my session, you're in the CS session, so you should have seen this 2001, right? It's called a parse tree. And if you're in the engineering section, that's okay, but it's something for the background. You may want to look it up in the Wikipedia or somewhere. It's actually a very simple concept. Okay. Okay, so that's about the composite structure over here. And now our problem really is, let's say for this particular tree, okay? So that's our tree for 341 plus 2. 341 plus 2. Let's say given this particular expression at the runtime, we want to perform various operations on that. We may want to evaluate, in which case we'll get 343, right? That's one possibility. Or you may want to print prefix. I'm not sure how many of you actually have seen prefix notation, but it simply means operator first and then operands later. Okay, so you can think about this is the prefix notation. And of course, this is infix. Okay, you can also print postfix. Postfix means operands first and then operator last, right? So this will be 341 and then 2 and then plus. Okay, just different ways of pretty printing. So, but apparently there are various operations, right? They're different. And also you want to do type checking. So type checking is basically what your programming IDE would do for Eclipse or for iPhone Studio or for Visual Studio if you program in C#. So type checking simply means you are actually manipulating values in a good way. Okay. For example, what would be one example where it's not type correct? For example, if you say 341 and then let's say and true. Let's say if you put this expression here in iPhone Studio, this will tell you it's not type correct because this is a logical AND conjunction. So that means the left hand side and the right hand side must be Boolean. Right hand side is a Boolean, that's good, but the left hand side is not a Boolean, so this is not type correct. Okay, so this is not type correct. Okay, so now we can also try to do type checking like that. Okay, in this particular case, because we have a numerical operation addition called plus, and then the left hand side and also the right hand side, they are both integers. So in that case, it would be type correct. So that would be, for example, just say true. Okay, so now you can see I've gone over 1, 2, 3, and 4. 4 different operations over here, right? So of course, as you grow the language structure over here, maybe you're adding modulo, you're adding maybe the relational operation, logical operation, etc. And also for the for this particular base case, you're also adding Boolean, you're adding integer, you're adding real number, and also string value. So expression language can become very rich. Okay, anyway, back to the original question for motivating problem. How can we support 1, 2, 3, and also 4? How can we support all these 4 operations over here? Okay, so now let me tell you from what we learned from last time, right? Let me follow a very similar design pattern over here. According to the composite design pattern for equipment and also for furniture, every time you want to calculate something, you will simply put the operation at the root of the hierarchy. That's why I mentioned that just a few minutes ago, right? There's a reason for that. So now, if we simply follow this particular pattern over here, so what I will do now is I'm just going to put, let's say here, I will put evaluates over here. Okay, I would say evaluate is simply deferred at this level over here. So that will make sure evaluate will be forced to be implemented over here. And also evaluates has to be implemented over here. Okay, so the first one, like a price. Let me use a different color here. Also, I have print, let's say prefix. And that's also defer at the expression level. And then that will force me to also say print prefix. And that'll be effective, right? And also print prefix. Okay, you can see what I'm going. Okay, let me just put down the remaining 2 very quickly. Okay, and also we got also here print postfix, deferred, and also print postfix. print postfix. Okay, you can see as many as we like. Finally, let me use orange here. Okay, type check. So I'll just say TC, type check, and also type check, and also type check. Okay, so this is really following what we learned from the composite design pattern. The overall structure for the composite, you can see we got either base case or we got recursive case. That part there is not really problematic. I would say that one's fine. But now, the fact that as the number of operation we want to perform on the tree grows, every time when we add a new operation, we actually have to declare that over here, for example, type checking, and then we got to also we got to define that effected, make it effective, adding implementation for every effective class, right? So now, question for you: any design principle we are violating over here by following this? Okay, so now let me write it down to say, as the number of operations grows, increases, okay, do we violate any design principles? Okay, that's my question. Okay, I heard from Jean, you said single choice principle. That's actually the correct answer, but can you tell me why? Okay, single choice principle is definitely one of them. So maybe I should say principles. Okay, it could be several of them. Okay, what Jean said was actually correct. It's a single choice principle being violated. Actually, it's quite obvious. Okay, I'll help you out very quickly. Okay, maybe you're typing, but I'll just help you out. Over here, you can think about single choice principle tells you every time you are trying to make a change, for example, let's say for type checking. Let's say if I decide I want to maybe just for some reason, I want to change, just think a little bit more abstractly. Maybe abstractly, I want to just modify my type checking maybe a little bit, okay, for whatever change I want to make. How many places do I need to go to modify it? Apparently, number one and number two, more than one places. So that means that more than one classes you actually have to modify whenever you want to make a change. Okay, let me give you a little bit more concrete example over here. Let's say print prefix over here. Let's say if currently the way I print it is simply say plus 331, and also I have 2 over here, for example, right? Let's say I want to modify my pretty printing for prefix. Let's say I want to modify my prefix printing into, rather than this, I want to add parentheses just to show the order of evaluation. I want to say add parentheses over here and plus over here and add this over here and add this over here. Let's say, for example, right? It's just one possible change. But now, how many places do I need to modify to really change this pretty printing prefix? Well, apparently, you want to modify not only at the integer constant level, but also you want to modify at the plus level, right? So now you have to modify both over here and also over here. Okay, so that's violating single choice principle. Okay, so now, okay, I'll say number one, single choice principle. Single choice principle. Okay, that's definitely the case. Is there any other design principle we are violating? That one is maybe slightly less obvious, slightly less. Anybody want to try? What's the second principle we are violating? Should I give you a little bit hints? Think it this way, okay? But of course, sometimes you may actually forget about the name of the design principle, maybe, but you can still see what's going on over here. Let's say this. If I got evaluates over here, let's say in a single class, right? It's a single class over here. A very important design principle is you don't want to create a Superman class, right? Everything that's included in the current class should be relevant to each other, right? Here we got evaluates, we got pretty printing, and also we got another pretty printing. And then we got something that doesn't seem to be so relevant called type checking, right? Maybe later on, I want to support another operation. For example, I want to say cogeneration. Okay, let's say generates. Let's say maybe I want to go from the programming language into assembly code, for example, MISP, like what you learned in 2031. Generate MISP. So this is just another operation I want to support, right? So generate MISP and also generate MISP. But now you can see I got so many operations over here, right? Over here, it seems like they can be divided into different categories like this. Category number 1 is about printing. Category number 2 is about evaluation. Right? I'm pretty sure you will agree. Evaluation is actually not quite the same task as printing, right? One is about to print the tree. The other one is about traversing the tree and accumulate certain value. So they're not really the same operation. Number 3 is about cogeneration. Of course, generating MISP is just one example. You can also generate C code, or you can generate Java code if you want to build a compiler from IFO into Java. Okay, I'm not sure why, but maybe you want to do it. Okay, so now you can see we can at least see 1, 2, and 3 categories over here. And now these categories are not, okay, relevant to each other. So our conclusion is, it seems like if you keep you're trying to follow this particular strategy, every time you want to add a new operation, you will simply add it to the root class of the hierarchy. Then you can create just more and more categories of operation that are not relevant to each other in a single class. So what design principle do we violate over here? So now hopefully with my hints, you can now see what the keyword is that we are violating. Anybody? What's the design principle? Should I give you a little bit more hints? Something starting with, aha, Joy, you got it right, cohesion. Exactly. So cohesion is really the design principle that's being violated here, right? Okay, that's now violated. Simply because, as I try to illustrate, you got, in principle, many categories of operations which are not consistent with each other. They are now grouped into the same single class. So that's violating cohesion. Okay. Okay, guys, let's summarize what we have seen so far. We haven't talked about visitor just yet. We're just talking about without using visitor, what would be the problem, right? The problem is you will violate both single choice principle, as I just explained in the first half, and also you will also violate cohesion. So these are the two design principles you will violate if you try to group all the operations in the root class of the hierarchy. Okay, let's go over the slides very quickly, and then we'll be ready for visitor very soon. Okay, that's basically what I illustrated on the iPad. You can also see that on the slides. And also distributing unrelated operation, right? That's a violation for single choice principle and also cohesion, right? So these 2 points have been already explained in the iPad. Okay, you can review them as well. So now, before we go to the visitor pattern, so there's one more design principle we want to talk about. Okay, it's called open-close principle. And if you look at the name literally, it seems to be contradicting. How can a single system be both open and closed? And because open and closed, they seem to be antonym to each other, right? But it's actually just one design principle. Let's go over the design principle very quickly together, and then we will be ready for going over visitor. Okay. So now, software entities, like for your classes and features, should be both open for extension. Okay. So what I mean by that is, let me just try to draw some picture for you at the same time. Okay. So now, thinking this way, right? We talk about open-close principle. Apparently, there will be 2 parts for the principle. Okay, open-close principle over here. Imagine that this is your system. Okay, so now we are saying that one part of your system should be open, the open part. Okay, And the open part, the open part should be open for extension, which means any extensions you want to extension. Any extension, for example, maybe a new operation. Let's say for our particular case, let's say this, right? If you look at our language over here, what can be the potential extension? It could be one new operation, for example, cogeneration. Okay, that's example number one. Or it could be example number two. Another new possible extension would be, what if, let's say, currently we only have addition over here. We want to add one more binary operation, maybe multiplication, for example, right? So now we can say a new binary operation. Okay, so now it could be, for example, multiplication. So these are just two possible extensions. It can be either new operation you want to perform on the language itself, or it can be a new language operation like a binary operation, right? Like a multiplication. Okay, so it can be two possible extension. Okay, it should be open. And for the open part, I will just say green over here. I'm sure for those of you who might be thinking about, actually, so far, this particular principle looks similar to something we talked about before. Okay, I'll mention that at the end. But I can tell you they are not quite the same. Okay, I'll get there. Okay, so that's the open part, and then also close for modification, right? So close for modification is like this. Let me just say for the pink part over here. So this part should be the close part for your system. Okay, so now this simply means extension should not go here. Should not really go here, right? So you can see, basically extension, every time there's any extension, either, how about this? Can I just save my writing later? Let's say extension 1 is a new operation like a cogeneration. Extension number 2 is like a new binary operation like multiplication, right? And now, close over here is saying that every time if I want to have, let's say, extension number 1, that means it shouldn't go to this particular part of my system, okay? And or each time if I got also extension number 2, it should also not really go to this particular part of my system. Okay, I'm just talking about the principle in general. Okay, we have to pay more closer attention to our example later. I just want to tell you open and close. Okay, and then I will make the distinction a little bit more clear a little bit later. Okay, okay. So now we can extend and we can close. Okay, you can see also the written explanation over here. Okay. Okay, so now let's say talk about our particular application, but like expression language, right? This particular language over here. Again, okay, always remember the structure of the language. Okay, so now we're saying that if we want to apply for open-close principle, okay, let me just say one more thing. Whenever you got open, whenever you want to really ask, do we satisfy the open-close principle, right? Every time you're asking yourself, did I actually satisfy the open-close principle? Okay, so here is how you can judge, right? Yes, if there is a clear distinction about which part is open and which part is closed. Okay, so number 1 here. Okay, number 1, if you actually satisfy the open-close principle, if number 1, there is a clear distinction, right? So now, who should make that clear distinction? You as the designer, okay? Clear distinction about which part should be open and which part should be closed, right? Of course, you will put that maybe somewhere in your code comments or in your interface or somewhere in your documentation. You know, like the project report that you have to submit at the end of the day, right? Okay, number one, if there's a clear distinction. Number two, over there, at the runtime, oh, actually, how about this? Number two, overtime. When I say overtime, which means from extension to extension for your projects, right? Over time, the closed part, let me say that more precisely. The overtime, the open part should be touched when there is an extension, right? So here I'm saying whenever there is any extension for your software, whenever there's any extension there, it should be touching the open part, right? Not the closed part. So let me just write one more thing, and then we can go back to our example. Okay, the closed part should be touched, I would say, very rarely. If not, never. Okay, I'm just talking about principle over here, and then we're gonna see how we can apply open-close principle to our particular problem for the language. Okay. Anyway, let me go back here. So let's say for our particular example over here, if we want to apply open-close principle, so now we want to decide which part of the system should be open and which part of the system should be closed. Okay, let's see this. Okay, let me. There was one question from Meng Yuan. Okay, you say, does the supplier never touch closed part? Okay, over here, I would say, yes, that's correct. You're saying this. I would say here, when I say very rarely, okay, over here, I really meant for the supplier. I would say yes. That's correct. So once you decide what this particular part to really represent a closed part of your system, okay, or at least you say this particular subsystem of your system is actually closed. That means you should once you define that, you should really touch it. Rarely. Oh, if you very occasionally touch it, that's fine. But if you touch it too often, then that's violating open close principle. Okay. Okay, so let me go back there, and then let's talk about the for our particular example here. Okay. So now either we got so which are the two parts for our particular language, right? So now let me just go back to our particular example here, and then before I talk about visitor, okay. Let's say this. For our particular example okay, let me switch iPad. Okay, again, we talk about open-close principle. And for our particular example, we actually got two scenarios, okay? First of all, we got two parts for the system. If you look at that, okay, let me go back here. Again, this is the design that we agree is actually not obeying single choice principle and also cohesion, right? But there are two parts for this particular system. Either we talk about structure, okay? What are the structure? We got structure is really the composite design pattern. We got expression, under which we got base case and we got recursive case. That's the structure, composite, okay? And also we got operations. Operation will be evaluate, pre-printing, and also type checking and code generation. So it's either structure or language operation, right? So two parts. Let me put it there. So now I'm going to say here. So one is about the language structure. So that's the first part of your system. The other part is the language operation. Okay, language structure, I'll just give you one example. For example, the plus, right? Addition. And also language operation could be, for example, code generation. Okay? Okay, we got two parts for the system. Okay? So now, if we talk about open-close principle, Open close principle does not constrain which part exactly must be open or closed. It simply say for you as a designer, you have to commit a choice. Okay, so now you wouldn't make both of them open or both of them closed. You want to say maybe for your particular application, you want to say maybe one part should be open, the other part should be closed, right? So now, how many possibility do we have? I'm pretty sure you will know two possibility. Either one want to say maybe the language structure part should be open. Okay, I'll talk about the consequence of that in just one moment. Or you want to say the language operation part should be open. So green means open, right? And accordingly, you can see for the first alternative over here, you can see because the language structure part is open, so the language operation over here is closed. And now, accordingly, it's the second alternative, right? So now, let me just be consistent. Language structure, oh, that's good. Okay, so this is alternative number 1. And this is alternative number 2. Both of them satisfy the open-close principle, because in both alternatives, I commit that one part should be open and the other part, accordingly, should be closed. Okay, so now let's go a little bit further. Okay, so guys, so far so good? Okay, open-close principle again tells you, you as the designer, you have to commit. One part should be open, doesn't matter which part, but the other part should be closed. Okay, let's now talk about these two alternatives very quickly. Okay, and then we'll see the visitor pattern actually assumes you actually choose one of the alternative. I'll tell you which one in just a moment. Okay, the visitor pattern is only applicable if one of the alternative is satisfied. How about that? So later on, we're going to talk about the visitor design pattern. And now, in order for visitor design pattern to really work, think about what would be the working scenario for visitor pattern. In order for visitor pattern to work, either alternative one of this or this must work. I'll tell you which one in just one moment. Okay, just one of them, exactly only one. Okay, so now let's talk about the two different alternatives, right? So now let's talk about alternative number 1. For alternative number 1, we're basically saying the structure over here is actually open. The structure over here is open. So that means if we commit to this particular choice, we know that the only kind of extension we might make is on the open part, which is the structure, which means later on we might, let's say this. If we already got these operations, and let's say we already got this structure, let's say that's our starting point for both alternative, right? So we got actually constant, we got addition, we only got 2 possible language structure. And also we got evaluate, pre-printing, and also type checking. We only got these. That's a starting point, okay? Let me just undo. Okay, so now when we choose alternative number 1, okay, let's say that's one of the choice we commit to. So now let's say the structure part is open. So that means we are going to keep this part stable. And we don't really know extension to this, because this part over here is simply just closed, right, for operation, right? That's alternative number 1. We'll talk about alternative number 2, the opposite way, in the next slides. Okay, and now if this part is simply just open, what does that mean? That means you can feel free to, let's say I can add maybe one more class over here, let's say multiplication, effective, and then of course I will have multiple inheritance goes like this. Of course, you may have the standalone composite class as we learned from the composite design pattern. That's okay. And also similarly, you can have another one over here. Maybe you can call that maybe Boolean constant rather than integer constant. And this one also inherits from expression. So either this or this. So these are the extension for this particular structure. That would be legitimate, right? On the other hand, so now, according to alternative number 1, it would be unacceptable if we say we want to add a new operation to the closed part. For example, if we want to add code generation, for example, right? It's a new operation. So this would not be acceptable. Not acceptable because it requires change to the close part. Okay, let me summarize very quickly, right? So basically, open-close principle tells you, for you as a designer, you have to commit to one choice. Let's say if currently the choice I'm committing to is alternative number 1, which means the structure should be closed and also the operation should be, structure should be open and operation should be closed. So that means this kind of a change to the structure is only affecting the open part. So that's acceptable. On the other hand, if I'm trying to add in one more operation over here, it's touching the closed part. So that's unacceptable, right? It's really relative to which alternative you're choosing. Okay, so once again, okay. Similarly, so now let's discuss alternative number 2 very quickly in a very symmetric way. So now let's say for alternative number 2, the open part is now the operation and the closed part is actually a structure. Which means if I'm trying to do, let's say me as a designer, because I want to satisfy open-close principle, I commit to alternative number 2. In that case, that tells me I think it should be quite rare I should really change the structure of my language, right? That's why I make that such change. If I knew that in the future, it should be very rare that I should really modify the structure of this language over here, then I should really commit to alternative number 2. So that means if I try to make a similar change as I did previously, right? So now it would be considered as unacceptable because now the context changes, right? So now let's say multiplication over here, and now, or similarly, if I got Boolean constant over here, that's also inheriting from this, right? So these two, okay? So these two, they are unacceptable. And for a similar reason, because we are touching the closed part. And now this closed part, because now we are talking about a different alternative, so now the closed part is different. Touching closed part, which is exactly over here, right? It's a structure. On the other hand, what was considered as unacceptable in the first alternative is now the opposite. It will be acceptable for the second alternative. So now if we try to say add cogeneration over here, so now this will be okay because now we are touching the open part. Okay, I would say you really want to review this design principle over here. Again, the design principle doesn't really tell you which alternative you should choose. Choosing either this or this doesn't matter as long as you stick to it. Okay, as long as you have some judgment, some proper justification for why you choose that particular alternative. Okay, that's one. And number 2, which one should be applicable to your visit pattern that we're going to talk about? Okay, so now let me tell you, it is the second alternative that's actually going to be applicable. Okay, alternative number 2. So this is the working context for the visitor design pattern, which means the following. If we haven't really even talked about the visitor just yet, we will in just a moment. Every time before you decide that you're going to apply the visitor design pattern for your projects, you should always consider, number 1, open-close principle. Number 1, think about whether your system, the language structure, the structure of your composite is going to be open or closed. And also accordingly, the operation to operate on the tree, should it be open or closed? If you end up having this particular alternative number 2, then that means visitor design pattern is the way to go. On the other hand, if it turns out for your particular system, you don't think the structure of your tree is going to remain stable, which means it's going to be open. In that case, visitor is not the way to go. Okay, so now let me go back here. Okay, so again, alternative number 2, this is for the visitor pattern. On the other hand, over here, alternative number 1, if this was judged to be the case, do not use visitor. Okay, so that's about everything we need as a background for visitor. Okay, any questions? So far, we haven't talked about visitor just yet. We only talk about the composite. Composite and also open closed. Guys, any questions or any clarification you might need? Okay, I think for the open closed principle, I talk about quite a bit of details, so you may want to review the lecture maybe before next time. But today we only cover part of the visitor just today. Okay, let me answer the question here for Christine about the second alternative. Okay, I said, let me just say that again. You said operation should be covered under open, but when you add multiplication, you said it's unacceptable. Okay, so let's say this. Okay, I'm not sure, maybe I did say something wrong. Okay, but let me just clarify, okay, just in case. So we got two alternatives. Okay, alternative number one, the structure should be open. That is why this, adding this and adding this will be acceptable. Okay, and also on the other hand, because operation is closed, so adding a new cogeneration operation over here should be unacceptable. Okay, that's alternative number one. Your question was about alternative number two. Let's see that. Okay, let me clarify. For alternative number two over here, okay, so now structure should be closed for this opposite alternative. So now in this case, adding either multiplication or let's say Boolean constant, so these are touching the structure, which is closed. So these are unacceptable, right? That's what I said over here. On the other hand, if you're adding a new operation over here, because it's supposed to be open, let's say over here, operation, let's say I'm adding cogeneration, so it should be acceptable, right? That's why I say the check mark, okay? Okay, it should be acceptable. Okay, very good. And then, oh, okay, from G, you're saying, how do we solve the cohesion and single choice principle? Well, we need a visitor pattern, okay? You can think about what we just said was like this, okay? Just one more clarification, right? Think about abstractly. You are basically thinking about this. Let's say I want to apply the visitor pattern. Okay, I'm thinking abstractly, right? And then let's say this is my particular application, right? Given my particular application, I want to apply the visitor design pattern, right? Before you can do that, you have the precondition over here. The precondition is alternative number two. More precisely, structure should be closed. Operation should be open. Operations should be open, okay? And now, of course, for the implementation, you can just apply the visitor pattern, which we'll talk about how you can do it, right? So now, in short part, if you talk about it, it's more like a single choice principle is satisfied, and also cohesion is satisfied, okay? So now, what we just talked about so far was really about what would be the precondition for applying the visitor pattern. Also, we talk about after the visitor pattern, you will see single choice principle as well as cohesion will be satisfied. So now what's left will be how we can apply the visitor pattern, right? That's what's left. Okay, hopefully that answered your question. Okay, another question here. We want to be able to modify both structure and operation for a language. Okay, so Minesh actually got another good question here. He's thinking that over here, I'm only giving you these two choices, right? I'm saying over here, I'm saying I talk about structure and also talk about operation. I say either this should be open or this should be open, right? You're basically talking about another possibility, which is like this. Okay, so now let's say this. You're saying maybe the structure should be open and also the operation should be open as well. That's what you're saying. Okay, I didn't include this possibility because it shouldn't be, well, when I say one part is open, I'm saying it should be relatively more, it's more like a relative. So when I say one is open, the other one is closed, that means the open part is more subject to changes, more subject to extensions. So in this case, you wouldn't say the whole system is completely open. That's not the way to go, right? You want to split them into different parts. And then I will try to address your question later, because you're saying, is it possible to have a good solution where the structure and the operation are both open? I can tell you that it's kind of beyond the scope for this particular lecture, because for the visitor pattern that people have been using quite commonly, you don't actually want the structure to be open, which I will explain. Okay, maybe I'll return to you this particular question a bit later. Okay, so we can just talk about visitor first. But for now, I think for simplicity, let's say either this or that. Okay, keeping the whole system open, which means nothing is stable and closed, is not the way to go. Okay, I'll get back to that question a bit later. Okay, we got about maybe 20 minutes or 10 or 15 minutes, right? I don't think I can finish the whole design pattern for visitor today, but I would suggest at least we go over the architecture so I can trace the code together with you next time. Okay, maybe that's the way. Okay, so now let's talk about the visitor. Okay, alternative number 1 and number 2. How about visitor pattern? Okay, and for visitor pattern, we'll go over the textual description next time, okay? And then we're gonna see how exactly we can satisfy open-close principle next time. But now, this will be the architecture for the visitor pattern, okay? It's actually quite a very interesting pattern that you have to put some thoughts into it, okay? Let's see. So maybe I'll just spend the next 10 to 15 minutes just talk about the architecture and also how you can use it. And then next time we'll trace the code. And then there's something very important about visitor pattern, which is called double dispatch. Okay, I'll mention the term just now. Okay, those of you who might be interested, you can actually preview the slides before Wednesday. It's called double dispatch. And double dispatch simply means by calling one particular method, dynamic binding is going to occur 2 times. That's why it's called double dispatch. Okay, we'll get to double dispatch next time. Okay, for now, I'm just going to talk about the visitor pattern and how we can use it. That's it. Okay, hopefully within 15 minutes, I can finish that. Okay, and then we'll talk about the details next time. The visitor design pattern, let me just focus your attention here. Okay, so now you can see overall there are actually 2 clusters over here, right? You can see this is cluster number 1, this is cluster number 2. Okay, and now first of all, let's look at the cluster name. You can see this part over here is called expression language. Okay, and this part should be the closed part. Right? Remember open close principle. And for visitor design pattern, I want you to refer to alternative number 2. Okay, so now the language structure should be closed, whereas over here where you got expression operation over here, this part here should be open. Okay, this part here should be open. Okay, so now let's look at the closed part and open part separately. Okay, let's look at that. So now for the closed part over here, it's basically composite with one single extension. Okay, let's see that. So now if I look at the closed part here, you can see the top level I still got expression, right, which is deferred. Okay, and also I got my constant over here, and also I got my addition over here. Right, so these are the I'll talk about close and open maybe next time in a little bit more detail, but for now the only extension I need to add goes like this. Okay, now I say that in the top level expression, right, which is deferred, I'm adding one single new feature or command over there, which is called accept. So this simply means every time if I declare E of type expression, okay, and now whenever if I have static type of type expression or any of its descendant classes, I can say E dot accept. accept something over here. And what's the type of that something? It's of type visitor. Okay, so now, so you can see visitor over here is a supplier over here. We got client supplier because now for the parameter of the accept over here is of type visitor. So now that's why we got a client supplier relationship over here. You can see because of this declaration visitor here. So now we got this client supplier relationship here, right? So now you can see accept is going to go all the way to the other cluster. Okay, this is accept. Okay, so number one thing you should really remember is when you revisit this particular visitor pattern is the only extension we made on the composite side, which is about a composite language here, is adding this particular accept command, whose parameter type is visitor. So that will create this particular client supplier, which will go to visitor. Okay, hopefully so far so good. Okay, and now every time you want to call e.accept, you will simply pass some visitor objects over here. Some visitor. Some. Could be any of the descendant classes of the visitor class. Okay, any questions for now? So far, I only talk about the language part. I haven't talked about operation part, which I will. Okay. So now, I want to minimize this a little bit. Okay. Oh, by the way, for those of you who actually want to get a clearer, cleaner picture, go to lectures page. I just want to point to you. Okay. And then if you go to, for today, I'm going to upload more new stuff. But you can see for visitor bound diagram. Okay, you can see that diagram over here. Okay, you can also download it for yourself. Okay, so now I have a question for you. Let me phrase my question here. You can see over here, different question. Okay, two questions basically. I want you to look at this particular part, right? That's the visitor part. Expression operation. This part is supposed to be open, right? And now you can see for visitor over here, that one is deferred. Okay, we got some features over here, and also we got 1, 2, and 3. 3 different descendant classes. Okay, the number of features we have over here, and also the number of descendant classes we have here, they are not arbitrary. They somehow got determined by this side of the architecture over here. Okay, let me phrase my question more carefully. Okay, okay. So now here's is my question. How many descendants classes of visitor? And here, when I say the visitor, I don't necessarily really constrain to our particular example for this particular part. Not necessarily, but you can use this particular architecture as a hint. Okay. And also, how many commands, how many visit okay, I'll put a star here, which means can be visit constant, visit addition, etc. Right? How many visit commands in okay, these two questions are very important. Question number 1 and question number 2. So these two questions will somehow give you like a formula to actually tell you, given some composite design pattern to start with in the beginning, right? You can figure out exactly how your visitor structure should look like to begin with. That's my point. Okay. So now let me just tell you, in this particular case, you can see for the visitor class, we actually got 2 commands over here. We got visit constants and we got visit addition. And every one of them, their type, for example, when you say visit constant, your parameters simply say, I want to visit a constant. When you say visit addition, then the parameter will just be an addition accordingly, right? So now I'm asking in general, how many such visit commands should we have? In this case, we just have 2. But why 2? Why? Question number 1, okay? question number 2. In this particular case, we have evaluator, we have pretty printer, and also we got type checker, right? Hopefully you can see every one of them correspond to the concept of language operation, right? That's why we say expression operation over here. And then of course each one of them, you will simply inherit all the features, all the visit feature from the visitor. But now, how many descendant classes should we get in general? In this case, we get 1, 2, and 3. But why? So guys, hopefully you can see my question over here. Okay, that's maybe the first time you see the architecture over here. Okay, I'll pause just very quickly, right? I'll finish within 10 minutes. Okay, just bear with me. So I think question number 1 and question number 2 is very important because that really gives you, again, a formula to say, given the composite pattern, doesn't have to be language structure. It can be furniture structure. It can be your maybe equipment structure, right? Given that particular composite, you would know right away how many classes you would need to begin with and how many features you would need to begin with in your visitor cluster. Okay, that's something I want to carry forward before the end of today. Okay, Q1 and Q2. Okay, let's say this. Okay, how many descending classes of visitor? How do we determine that? First of all, how do we? Depends on how many what? Anybody want to try to answer? Okay, if you're struggling, that's okay. Okay, I will maybe allow you some time to study before Wednesday, but okay, let me tell you the answer. Okay, I see from Jim the type of attributes. Okay, type of attributes is not, maybe you mean the type of operations, right? Maybe that's what you meant. And Ken, thank you. You say the number of language operation, exactly. Okay, so now for question 1, how many descending classes you should really get for visitor in general? It depends on how many operations for the composite tree. And the tree over here could be maybe for your expression tree, or could be for the furniture tree. It can be for the equipment tree. Okay, very good. So now, what about question number 2? How many visit commands in visitor? For example, in this case, we got visitor, now we got visit constant, we got visit addition, right? Anyone want to try? Okay, so now, how many visit commands I need in my top level visitor depends on what? Question number 1, it depends on, right? For question number 1, it depends on how many operations I want to support for my language. What about question number 2? As many subclass, good, Minesh, you said for question number 2, as many subclasses of expression. But when you say as many subclasses, right? In that case, well, let's say this, for example, right? I'm just saying subclasses may not be so precise. For example, if I just got another class over here, I just call that maybe composite expression, which is deferred. You don't really want to count that one as well, just by default, right? So you want to say effective classes, right? So now, Ken, you said the number of language elements, I think that's more accurate. Okay, so now, let me just put it here. Depends on how many effective or implemented language element classes. So now in our case over here, you can see the only 2 are number 1 and number 2. 1 and 2. So that's why we got 1 and 2. Over here, okay, 2. Okay. So guys, let me take just maybe 3 more minutes. Okay. So now I would say before Wednesday, try to think about these 2 questions very carefully together. And now you're already ready to answer the following question. So why alternative number 2 must be chosen? Okay. Now I have a small exercise for you. I'm going to do it together with you next time. Okay. So now following alternative number 2 over here, for my visitor pattern, what if adding multiplication, okay, it's like a change to the close part, right? I want to add a new operation for multiplication, language structure. And number 2, what if adding code generation? I want to think about 1 and 2, and then for each one of them, think about how you will have to modify the architecture, the diagram over here, right? Either you got to touch this particular cluster, or you have to touch this particular cluster. And now, once you do that, you will see why. In this case, touching one of them will be considered as unacceptable. That's something we're going to see on Wednesday. Okay, before I end the lecture, let me just do very quickly some illustration for you. Okay, how do we use the visitor design pattern? Okay, we're going to have more detailed tracing on a Wednesday. Let me just spend about 1 or 2 minutes quickly. So this is a small test about how you can use the design pattern, right? The test expression evaluation over here. So let's say we got at C1 and C2 over here, and also we got expression, we got visitor. Okay, so this part over here is about building the tree. Okay, we'll visualize the tree next time, but you can also try visualizing yourself. And now, once you have built out a tree, at the top level, you simply got at. You can think about at is now pointing to some tree over here for this object, right? So now, the only thing you got to do is to say at dot accept v over here. And then, over here, v over here is simply just some visitor. And notice that for the visitor v over here, dynamic type, the dynamic type is simply just evaluator. Okay, and now I have one question for you. That will be my ending question for today. Okay, so now I want you to think about the following. Right, you can see over here the way I'm trying to retrieve the result for visiting the tree. Right, I'm trying to let's say this at over here. That one simply correspond to basically 1 plus 2. Basically, that's what it corresponds to. After, say, at the accept some evaluator, and now I want to retrieve from the evaluator the result. It should be 3. Okay, so here's my question for you. You can see the way I did it was by using some cast expression, right? I say I have to cast v into evaluator, right? And then I can say eval dot value over here, right? Okay, so here's my question for you. Okay, what if I simply say the following? Rather than saying eval dot value, so you can see eval over here is a cast version of the variable, right? But can I say, since I'm trying to accept v over here, can I simply say v dot value? Why would it not work? Why do I need to bother for this particular cast? Okay, think about this particular question over here. Think about if that will work. And if you want to find out the hints, you may actually want to look at the architecture over here. And then you can also look at the code that are included in the later slides. Okay, that's a question for you to think about. Okay, so now I'm gonna end the lecture over here. I know I'm running over time, but I just want to point out. Okay, so from for Wednesday, we're gonna finish the visitor design pattern, and then we'll start talking about the observer. Okay, so now again, I want to point out something very quickly. So not there. Just to mention to you, just bear with me, just 30 seconds, very quickly. My computer's running slow. Anyway, sorry. What I want to show you very quickly is this. Okay, just mention quickly, so the course evaluation is now online. So now for those of you who are in section M, I will encourage you to maybe speak up your mind in the course evaluation. Okay, hopefully you can do it before the deadline. All right, I'll see you on Wednesday.